Okay, today we're going to be talking about units and how units can be used in physics. First, we'd like to talk a little bit about the idea of SI units. We have the meter, which is unit of length, kilogram, unit of mass, and second, unit of time. We could use other units besides what's called the SI or Systems International, such as centimeters for length or feet for length, but we're going to pretty much stick with the SI units. We will do conversions between them, which I'll show you later in the video. All right, so mass, length, time are all what's called base units. Base units mean that you can't get simpler than that. For example, the length between 2 points. You can't get simpler than that. The duration of an event, like time, you can't get simpler than that. But if you use these together, you get what's called a derived unit. For example, if you take length and you divide it by time, you would have something like a length and you divide it by time, you would get a derived unit for velocity. Boy, that looks really bad, but you get the idea. We're also going to talk a little bit about converting from one unit to another. And some of these conversion factors are found in the inside cover of your book. For example, we may want to get from feet to meters or from horsepower to watts, which I'll show you in a moment. All right, let's look at the first example. The world's tallest waterfall is in Venezuela, Angeles Fall, and it has a total height of 979.0 meters. Now, you might be confused with the idea of 0.0, but as you learned from your chemistry class, the 0.0 is signifying that this number is red or significant to the 10th digit. You would have no problem with 979.1 or 0.2. You shouldn't really have a problem with it being 979.0. Anyhow, we know that 3.281 feet is the same thing as 1 meter. So that if we say that this is equal to this, it's numerically, if we divide them, equal to 1. So if we take 3.281 feet and divide it by 1 meter, it's the same thing as multiplying it by 1. So I could take this ratio and multiply it by any number and really not change it because I'm multiplying it by 1. I could do the same thing with the reciprocal as well. So let's see how we use that. We have a length of, once again, 979.0 meters, and we want to change that to feet. So how we're going to actually be doing that is we want to get rid of this meters here. And so we're going to multiply it by a conversion factor that's numerically equal to 1, because this is really the same as this. And we put meters on the bottom to cancel out with meters on the top, like so. So now we're left in feet. And as you can see, the feet are what we wanted to be in. So how do we actually do this? We would take 979.0 meters. Meters are gone. So 979 times 3.281. And you end up with that many feet. Okay. Sometimes the units we're going to be using are like really big or really small numbers. We could use scientific notation, or we could just change the prefix sometimes. For example, if you're going to measure the length from here to North Carolina, you probably wouldn't do it in inches, and you probably wouldn't even do it in feet, but you may do it in miles. The same thing is true with the SI system. You wouldn't measure from here to North Carolina in millimeters or meters. You would probably use kilometers. And if you have any problems with how to actually convert those, we'll be talking a little bit more about them in class, but I think everyone should be pretty familiar with changing from meters to centimeters and meters to kilometers and what have you. All right, so let's try another example. Let's say you have 65 miles an hour and you want to change it to meters per second, okay? And we have these conversion factors, okay, like feet into miles, seconds into hours, and feet into meters, okay? So, let's look at this again. We have the idea of 65 miles per hour, but we don't want miles. So we cross out miles on top and put miles on the bottom, and we use the conversion factor of how many feet are per mile. but we don't want hours either. So we cross out hours with hours, and now we're left in feet per second, 95 feet per second. Now we could do this all as one continuous problem, but what I like to do is, just to show it as a separate step, I would like to go now from feet to seconds, feet per second, into meters per second. So now I have to do a second conversion from 95 feet per second into meters per second. Now I could have done this all as one step, but I wanted to show you that you can break it up any way you want to. So right now once again we're in 95 feet per second, but we don't want feet per second, we want meters per second. So we need to get rid of feet, which is on top, and get rid of it by putting feet on the bottom. As they cancel out, you can see that now we're left in meters per second, and you simply take 95 and divide it by 3.21. Technically, you're taking 95 times 1, dividing it by 3.21, and it comes out to be 29 meters per second. Okay. Dimensional analysis. We can actually use dimensional analysis to check to see if equations are correct as well. We do not use the idea of meters or kilograms or seconds in this time. We're just going to use the basic base unit of length, mass, and time. In this example, we're actually only using length and time. What I like to do is see if this following equation is correct. We have x, which is unit of length, is equal to 1/2 vt squared. Is this correct? Well, let's look. X is a unit of length, so I'll put length in, equals. Now there's no units for 1/2. Speed, length per unit of time, but it's squared, so t squared. And if you look at the algebra here, all the t's don't cancel because there's 2 on top and only 1 on the bottom, so you're left with L times t, which proves to us that L is not equal to L times t, so this equation is indeed incorrect. Now, even if the units did come out correct, like if I just got rid of this squared and had 1/2 vt, it would have worked out correct, but it doesn't prove that the equation is actually correct. Look at it from this point. Maybe this should have been 3/4 or 5/8. We don't really know. Using dimensional analysis will only actually prove if an equation is wrong. It will never prove that it's right. Let's try another example. Is the following equation dimensionally correct? Length is equal to velocity times time. So once again, using the same idea, we have length in L for the distance, velocity or speed as length per unit of time, times a unit of time. Does this indeed work? Let's give it a shot. The t crosses out with the t, and we're left with length equals length, and it is indeed correct. So just to clear this up a little bit, using dimensional analysis will never prove whether an equation is correct, but it could prove that it's incorrect. Okay? And that will be it.